Now we will be talking about Coulomb's law, and this Coulomb's law is actually an empirical relation. By an empirical relation, I mean it's a relation that has been found experimentally by doing experiment. The Coulomb's law was discovered by Charles Coulomb in the 19th century using an apparatus similar to this. He had two small objects which carry charges and he tried to observe on what factors does the force between these two objects depend. And he came up with the following findings. He said that this force depends inversely on the square of the separation between the two charges. If the separation is r, so it goes like 1 over r square. So this is the first observation. And the second is that the force is proportional to the product of the two, the magnitude of the two charges. So the magnitude of the force is proportional, increases as Q1, Q2, which is the product of these two charges, increase. And now, after his work, we know now that the electrostatic force, we call it electrostatic force, between two point charges is actually given by Coulomb's law, the relation that he put forward. Now, the point, we need to explain what do we mean by a point charge. A point charge actually refers to a particle of zero size that carries an electric charge. So it's a particle of zero size. In reality, in physics, there is nothing that is of zero size. Everything has a size in physics, even if it is small. So this is a mathematical idealization, actually. So then what is a real point charge is? Actually, a point charge is an approximation. When we have particles carrying charges so that the distances between them are much larger than the dimensions of these particles, then we can approximate these as point charges. Now, this is just similar somehow to everyday life experience. When you look at an object from far, you start seeing it as small. So it's like you can approximate it by a point. Okay, so this is the meaning of a point charge. It's actually an approximation. Of course, today we know also that the electrostatic force, or the Coulomb's force between point charges, is a conservative force. This applies in general to the electric force, and as we will see shortly, to the electric field. Now let's formulate this mathematically. Well, mathematically, Coulomb's law assumes this form. Here, this is the magnitude of the charge, so you don't see a vector. It's not bold, there is no vector sign on it. This is the magnitude of the force between charges Q1 and Q2 that are a distance r apart. So as you can see, this force, the magnitude of this force increases as this product increases. Now we put these as absolute values. So even if the charges are, one of the charges is positive, or the other is negative, or both are negative in this case, this is irrelevant, the magnitude of the charge. So you take the absolute value, because this is a magnitude of a force, it's a magnitude of a vector, and the magnitude of a vector should always be positive, as you know, or zero. Now, this is the distance between them, so this is in the denominator, and f increases with the increase of this product and decreases as 1 over r square. So this is the mathematical formula that gives us the magnitude of Coulomb's force between two particles. Now, when you we usually measure the charges in Coulomb, in units of Coulomb, and when this is measured in Coulombs, then this Ke is a constant called the Coulomb constant, and it is given as 1 over 4 pi epsilon naught. So it's given in terms of another constant. This constant is roughly 9 times 10 to the power 9 Newton meter square per Coulomb square. Now, this epsilon naught, which enters into the definition of Ke, is called the permittivity of free space. So this is the expression that we use. This is the value that it has in free space, or in air also. It has the same value. Now, if the charges are immersed in a medium other than air or space, then in this case you have to replace epsilon naught here, the permittivity of free space, with the permittivity of that medium. Now, so you have to keep in mind that in applying Coulomb's law, you use the charges in Coulomb. Of course, Coulomb is usually a large quantity, so we use mainly charges in microcoulombs, sometimes nanocoulombs, and we have to keep in mind that the force is a vector, because the force is by default a vector quantity. So now it is time to see how we can express Coulomb's law as a vector form, in the vector form. To do this, consider this figure where we have here two charges and point charges, and for the time being we take these two charges to be of the same sign, and we take them to be both positive. So we have Q1 and Q2. Now we want to find an expression for the force by 1 on 2, which we call it F12, or by 2 on 1, which is F21. Okay, so this is this is how we understand the indices here. So F12 is the force by 1 on 2, F21 is the force by F2 on 1. So to see how we do this, now let's first, from our knowledge of the nature of the electrostatic force, draw the vectors showing these forces. Now, according to Coulomb's observation, Coulomb's law, the force is, or Coulomb's observation, or what we know experimentally, the force, if these have the same sign, then F12, they exchange a repulsive force. So F12 is directed from 1 to 2, F21 is directed from 2 to 1, and along R, which is R, the separation between these two. So this is F12, the force by 1 and 2. This is F21, the force by 2 on 1. Now, if I want to express this in a vector form, in a single formula, what I do? I need to introduce a quantity, which is the unit vector r hat 1, 2. Now, this is a vector, so it has a hat, tells you that it's unit vector, which means it has magnitude 1. So if I want to find an expression, write a vector expression for the force by, for F12, which is the force by 1 and 2, then in this case, I introduce a unit vector, r hat 1, 2, which goes from 1 to 2. This is that unit vector. And I write F12 as this expression multiplying by r hat 1, 2. Now, how does this differ from the expression, the previous expression that I had here? Sorry. Now, I note that in the vector case, I don't have these absolute values. So if you look here, you can see I don't have an absolute value written here. Okay. So what the meaning of this is that the charges here, this expression here, might be positive or negative depending on the charges. If the charges are the same, are like, then it will be positive. If the charges have different signs, this will be negative. Okay, so this is the important thing. So this is how you express it. And in this case, this is a vector, which is, if this quantity is positive, then it is directed along r hat 1, 2. Because, you know, when you multiply unit vector by a positive scalar, then in this case, the result is a vector in the same direction as r hat 1, 2. If this quantity is negative, then the force is opposite to r hat 1, 2. Okay? And this is exactly what we expect, because when the charges are the same, when both are either positive or they are both negative, then in this case, F12 will be, which is force by 1 on 2, will be in this direction. So it's along r hat 1, 2. This quantity will be positive, and this expression will achieve that. However, if you have, for example, a positive and negative charge, then F12 will be in this direction. So it will be directed from 2 to 1. So in this case, this quantity will be negative, and so you will have a negative number multiplying r hat 1, 2. So definitely the force, this will tell you that the force is opposite to r hat 1, 2. If you want to find F21, then in this case you have to define a unit vector that goes from 2 to 1 in this case. And the expression for that vector is the same. Of course, this is a very compact way and efficient and precise way to write the force by charge 1 on charge 2 compactly and precisely. In practical applications, when you apply Coulomb's law to do computations, you usually do not use this unit vector form, but you work the magnitudes and then you try to take care of the directions using different formulas. We'll show you how to do this when we consider some examples about the application of Coulomb's law. So this is just what we have said. Now, another important thing about Coulomb's law that we need to keep in mind is that, Coulomb's force is force. So this means that, like any other force, it obeys Newton's third law. And this tells you that F12 is equal to F21 minus F21. So this is, what does it mean? That is, the force by 1 on 2, for example, is equal and opposite to the force by 2 on 1. Okay? So these are an action-reaction pair. And this is something that we keep in mind. Now, this is a checkpoint to check your understanding of the Coulomb's law and its vector nature. So please try to work out this checkpoint. Now, what if we have multiple charges? If you have more than one charge, then distributed in space, and these charges will exchange forces. Now, the net force on each single charge will be the sum of the forces acting on that charge by all the other charges. And this means that you need to add, to find the forces on one charge, you need to add the forces by all other charges on that charge. Of course, this should be a vector sum because the force is a vector. Now, so the net force, for example, on a given, if you have a charge called Q1 and you have more than one charge, then the net force on Q1 is the sum of all the forces by all other charges on Q1. So as an example, assume I have four charges, Q1, Q2, Q3, Q4. Then in this case, F1 in this case is the net force on Q1. The net force on Q1 is the sum of the force F21, which is by charge 2 on charge 1, and F31, the force by 3 on 1, and F41, the force by 4 on 1. So this, when you add them together, you get the net force on F1. Now what will be, for example, try to write it down, what will be the expression for F3, for example, the net force on the unit charge, on the point charge 3 in this case. Okay, so what is F3? Try to write it in a similar expression. This is one more checkpoint also. Please try to do this. Now, we will talk now about how we can apply Coulomb's law to do some computations. So we will consider two examples. The first example will be about finding the force between two charges, two charged objects which have opposite charges, and we will work out in detail how we can find the net charge and so on, the net force. And the second is how to find the net force on one charge in a system of three charges that are located at the vertices of a triangle. We will work these in detail on the board now.